with a very attractive title, but in fact I don't trust any image, but okay. It's about image of Julia sets that we can trust.
Okay, thank you very much. Pode pagar tudo. Okay, so I hope to convince you that you can trust the image that we make. So this, I'd like to start by thanking the organizers for having me here. This is, I have this opportunity to talk about this work that I have been doing for several years now. This is joint work with my colleague Diego Nerhab and Jorge Stolf from Campinas and João Batista Oliveira from Porto Alegre. So the theme of my, okay, I'm going to see image, so we need. Okay, tá bom. So the theme of my talk is, can we trust this beautiful image that we have all seen of Julia sets, like this one? Let me just start by reviewing what Julia sets are. Julia sets arise when you try to describe the dynamics of a map. In this case, in the case that we're going to talk about is the quadratic map z squared plus c. And the basic question that we ask is what happens to the orbit of a point? Of course, two things can happen. The orbit can be unbounded, and in this case, they actually go to infinity. And so we call the set of starting points that have unbounded orbits the attraction basing of infinity. Or the orbit can be bounded, and in this case, by definition, the starting point is in the field Julia set. The Julia set itself is the common boundary between these two sets. Julia sets have several wonderful shapes, and the main dichotomy here is that the Julia set can be either connected or a Cantor set, and the Mandelbrot set classifies that. A point is in the Mandelbrot set when a 0 is in the corresponding field Julia set. So let's see a few images. And these images you can trust. So Julia sets can be a simple shape, not so simple shape, or they can be Cantor dust, like these ones. So these images you can trust, and I'll tell you why now. Why should you distrust this beautiful image that we have seen? These images typically are computed using this algorithm or algorithms like that. This is the famous escape time algorithm that anyone can implement, and several people have. And in this algorithm, you take a grid of points as starting points, and you compute orbits starting at these grid points. And you do that until they leave this disk around the origin that you can compute. This is called the escape disk. If an orbit leaves this disk, then it goes to infinity. Otherwise, it stays bounded forever. So you do that, and you paint, you assign a color to how long the orbit took to go outside the escape disk. So why should you distrust this image or this algorithm? The first point is that you're doing spatial sampling. You're only computing something on a grid, on a discrete grid of points. So what happens between the sample points? Can we be sure that the behavior stays the same? The other main point is that this kind of algorithm only computes partial orbits. A program cannot run forever, so we must set an arbitrary limit, which I called big N here, and you stop computing orbits after a certain number of points have been computed, say 1,000. And you cannot be sure that this number is large enough. And the third major problem in this algorithm is that you are subject to floating point errors. This is a quadratic map, So every time you raise a complex number to the power 2 or any power, you need more digits to represent the number. So in this case, you need twice the number of digits to represent a point, and you need to do that in an orbit. So you need an exponentially increasing number of digits. So this is why I say that we cannot trust these images, because it involves sampling, spatial sampling. We don't know whether the behavior between the grid points is typical. The other point is that the partial orbits that we compute may not be long enough. Perhaps if you just compute just one more point in the orbit, the orbit goes outside the escape circle. And the last point is that we cannot be sure whether rounding errors in the floating point arithmetic in the computer matter. I'm going to describe to you an algorithm that has no spatial sampling, does not compute any orbits, and is not subject to floating point errors. And our algorithm does not spatial sampling because it classifies whole rectangles in the complex plane. It does not perform functional iteration at all, so there are no orbits. We replace that by algorithms on a graph. And our algorithm is not subject to floating point errors. All our numbers are dyadic fractions of limited precision, and even the standard floating point, double precision floating point arithmetic in the machine is enough for computing huge images, like 1,000,000 pixels by 1,000,000 pixels. So what our algorithm does is to compute a quad-tree decomposition of the complex plane. This is a decomposition of the plane into rectangles that get smaller and smaller near the Julia set. And our algorithm assigns colors to these rectangles. The white rectangles are guaranteed to be in the attraction basing of infinity. The black rectangles are guaranteed to be in the field Julia set when there is an interior. And the gray rectangles are guaranteed to contain the Julia set. So this is a certified quad-tree decomposition of the complex plane. So this is a mathematical proof. So it is in this sense that you can trust the image that we compute. Our algorithm has three main features. One is refinement, that it gets better and better along time. The other two features have to do with how we explore these graph algorithms, and I'm going to talk to you about that in a minute. Let's see first the refinement, how our approximations get better and better as you compute more. So let's see an example. This is for C equals -1. And you start with a quad-tree and all gray leaves, all gray cells. And these gray cells are going to get colored, either white or black, or maybe remain gray if we don't know what to do with them. And the hope is that when you subdivide the cells, you can then classify them, give them the correct color. So let's go down a few levels. So second level, some cells have been painted white, and this is a proof. I mean, these 4 white squares there all go to, all orbits starting on these squares go to infinity. And the gray cells, we don't know anything up to now, so you keep on subdividing, and then you get more white cells, and then suddenly you get some black cells. And these black cells, this image here is a proof, actually, that all orbits starting on these black cells remain bounded forever. And you do that, loss of time, and you get a better approximation of the field Julia set. This is what you get. This is an image that you can trust. The white part are guaranteed to be in the attraction basing of infinity. The black part is guaranteed to be in the field Julia set. And there's a gray boundary there that we're going to see in a minute in detail that contains the Julia set. So let's see that again without the tree. So So the approximation gets better and better and better, and then you get this image. Like I said, this image you can trust.
So how are you checking at each step the new white versus the gray versus the...
Yes, I'm going to get to that in a minute. Okay, so this is the image, has three colors, white, black, and gray. The gray is here, and the gray area contains the Julia set in this case. So the second, to answer your question, the second feature of our algorithm is cell mapping. This is what replaces orbits. So in cell mapping, we build a graph, a directed graph that, that has the leaves of the quad trees as vertices. And we have edges leaving every gray leaf cell, and they go to other to other leaf cells. And to color a cell, we just compute the image of that cell once under the map.
That's my question. How are you computing the image? Because
And that's my last slide. We compute the image of the cell, and if it's outside the escape disk, then the cell is white. Otherwise, we add edges from the cell we're looking at to every leaf cell that the image intersects. This replaces orbits by a conservative estimate of the dynamics of the map. And this helps you, actually this avoids any floating point errors, because we only compute the image once. There's no function iteration. So to answer your question, how do we find the image? So some mapping starts like that. You start with a cell, and then you compute the image. The image in this case is not so difficult. It's just a curvilinear quadrilateral with parabolic arcs. But to make it simpler, we're going to replace that by a bounding box. And bounding box can be computed easily with interval arithmetic. Or in this case, this is even easier because the bounding box is given by the image of the 4 vertices. And then we take this red box, and we need to find the leaves that intersect the image. So we take this box and send it to the quad tree. And then we use the quad tree to find the leaves that intersect this red box. These are the leaves. So these are the cells that are going to get edges from the blue cell to it. The union of these red cells contains the exact image of the blue cell, and that's enough for our purposes. So our graph is built like that. For each cell, we compute an approximation, an upper bound for the exact image, and we add edges for all, from that cell to all those cells. Let's see some more examples of that. So for that cell, the image is outside the circle. For that cell, barely intersects the square. This one is outside, and so on. So you see here the actual image is a curvilinear quadrilateral, and then the cells that intersect the image of the blue cell. So this is the second ingredient in our algorithm, cell mapping. And the last one is label propagation, is how we color the gray cells white or black if we can. So in that step, we propagate white and black towards the gray cells. A gray cell becomes white when all paths from it in that graph that we just built go to white cells. This means that all orbits starting on that cell go to infinity eventually. Like I said, the graph is built, it's a conservative estimate of the real dynamics, but that's enough for us to prove this kind of theorem. A gray cell becomes black when there's no path from it that starts from it and goes to a white cell. If that happens, then all orbits start on it are bounded forever. So there's no function iteration here. There's no need for setting a limit to the number of iterations that we're going to make in our algorithm. So in this sense, we have replaced function iteration, which is costly and may introduce errors, by simple discrete graph traversals. Sorry. And this is how we avoid floating point errors as well. Let's see some more examples of this algorithm in action. I have these 5 examples here. They're different kind of shapes, and I'm going to see how the algorithm works on them. So the first one is a very easy one. It's one where C is in the main cardioid near the origin. So after 5 levels, you already have found a large black region, and once you have found a black region, you can just refine it very quickly. I'm doing refinements, but you cannot see, I guess. So after 14 levels, what you get is this image. Like I said, this image has 3 colors: a white color, a black color, and a gray color, and these are all guaranteed. So this is the actual Julia set for this C. Well, no. Yes.
Your rule for assigning black cell is that its image is inside gray cells.
No. Either in gray cells or in black cells, yes.
Okay. Suppose it's just gray cells. Gray cells are the undecided ones.
Yes.
So if you go inside gray cells, why does that guarantee that you're not going to escape eventually?
Because gray cells may be undecided just because it might go to a white one. But sometimes you just have a cycle, kind of cycle like that. Once you have a cycle like that, even if it's gray cells, then it's bounded forever. It's like that. So it's surprising that sometimes you just find these huge black areas.
Just to clarify, it's
Yes.
not that there's no path
Yes. So there's no way you can get.
from a cell to a white cell.
In the graph.
In the graph,
Yes.
not a single path. So it's going to be trapped forever. You can't escape.
A gray cell is not. Is
The whole graph,
That's right.
yes.
so but you don't know that in finite time.
No, you have a finite graph, and you follow the.
You do. A gray cell does not necessarily go to a white cell. It's just that we don't know at that resolution. Okay? Of course, the gray cells that are very near the Julia set, who have orbits going to white area and orbits going to the black area, but other ones not. So this is the field Julia set, and this is the Julia set for this order C. Is still inside the main cardioid. Let's see a more exciting example. This is a period 3 bulb. So it takes a while until it gets to a black region, and black region is not so big, but once you have a black region, then your convergence is faster. So that's what you get, and this is the Julia set. So Julia set in this case is contained in the union of these gray cells. Not all Julia sets have interior. This is one case where there's no black region, but the algorithm works anyway. So this is connected, but it has no interior. And the algorithm has a hard time in the middle there, but it gets better when you increase the resolution. And Julia set can even be not connected, and the algorithm works for that case as well. So this seems connected, but then now you know it's not connected. It's actually a Cantor set, so this is a very sort of misleading image, but it's correct. I mean, whatever is left, whatever there is of the Julia set is inside this gray region. So this quad tree that we build can be used for several things. Our main objective here was image generation, and we can, like I said, build very large images, 1 million by 1 million pixels. And you can build smaller images with anti-aliasing, which look much nicer. And you can use the quad tree for robustly classifying a point or a box in the plane. You just go down the quad tree and see if it lands on leaves of the same color. In that case, you can give a color, or you can classify the box or the point precisely. You can also use the quad tree for computing geometric properties of the Julia sets, like the fractal dimension, the area, in the case of the field Julia set, and the diameter. There are asymptotic expansions for the area and the fractal dimension. I'm going to show you an experiment for computing the area. Milner, in his book Dynamics in One Complex Variable, has this graph there that's used the asymptotic expansion that I showed in the previous slide, where he shows upper bounds for the field Julia sets when C is real. And we did that for a smaller interval of the real line, just the period to disk and the main cardioid. And for that, what we get is this graph. There's actually two graphs here, but you cannot see except for a little bit here on the lower left. They are very close, meaning that the estimates of the area are very close. Here's the actual error. The error is very low in the main cardioid, and it's a little bigger in the period 2 bulb, but still is very low. And there's these cusps in the bifurcation points. Our algorithm has some limitations. The main one is memory. This is a memory-hungry algorithm. The depth of the quad tree and the size of the graph that we need depend only on the available memory. So if you have more memory, you can go down more levels. We can go down like 19 levels. We did that for the area. This translates to huge images, like I said, 1 million by 1 million pixels. But that's only about 10 to the minus 6 in spatial resolution. So this limits the estimates that we can do for geometric properties. The second limitation that we need to explore a region that contains the escape disk. That's because we are describing the whole dynamics, not just a little bit. So since we're replacing orbits by these graph traversals, we need to have it all. So this severely limits the amount of zoom that we can make. And this limitation is inherent into this technique because F is transitive on the Julia set. And finally, the main limitation is that we don't have any proof that it converges. But all images that we do compute are proved. We just don't know that, well, we know in the sense that we've seen it happen, but we don't know mathematically that the gray area converges to the Julia set when you increase the resolution. As feature work, we can just extend this algorithm very easily to polynomials, to other polynomials, not just a quadratic one, because there are estimates for the escape radius given by Douadi, for example. And I'd like to do that for Newton methods, Julia set for Newton methods of polynomial equations. And in this case, there is no escape radius. Infinity is not an attractive point. And we need to find explicit regions around the zeros of the function to use as a bootstrap region. Just for fun, we did this panorama with many images. What you see here looks like the Mandelbrot set. Is a Mandelbrot set, but it's actually a Mandelbrot set made of Julia sets. So you can play that with that on the internet without having to wait for a long time to see or to compute any given Julia set. So typically what we get is a Julia set like that. Well, the gray here is red. And this image, like I said, are guaranteed. The white region starting point for orbits that go to infinity. The black regions are starting points of orbits that stay bounded forever. And the red ones contain the Julia set. Thank you very much.